Let's continue with our second topic. So by now we know how to protect our mapping of whatever name.org to an address. And this can be done in a secure way. So that's mainly what this DNS is about. The second part is how can we secure our routing process. And we know that routing, well, that is something that the BGP is about, our exterior gateway protocol, connecting the different autonomous systems when it comes to routing, finding a path, etc. So what is routing about? You remember, routing should enable reachability. That's the idea. So we have to find a path. We have to find a path to a certain destination so that we can reach it from a sender. So this is where we have BGP, and BGP tells us based on a certain prefix how the path looks like. Okay, so that's the idea. So what can go wrong? Well, things could go wrong somewhere in between, in some intermediate systems and routers, etc. Yes, they could fail, but we can also have a problem in BGP itself, in the protocol, in the paths. So many different problems may appear. We know that if routers fail, then we start rerouting. We have maybe additional paths with different priorities, and so on. So if a protocol has a problem, BGP, we have to restart something, though we can handle this. But what happens if the path itself is wrong? So why should we care about the path? Well, the problem is if we tweak the updates in BGP, for example, we announce wrong paths, we can break easily service availability, though the path can lead to nowhere. So if I claim that I know the perfect path to a big service, Amazon or YouTube, whatever, but I don't have it, and everyone redirects the traffic via my AS, well, the service is not available anymore. So any end-to-end protection can't help here. We may also break certain privacy. So for example, if you say, okay, this traffic should stay within a certain country or whatever, and then if you reroute this traffic outside the country, there might be a problem. So an example. We know roughly now how the internet looks like with the autonomous systems, and we know that certain prefixes belong to a certain autonomous system. And we know when there's a customer, we know how to reach a certain prefix. So in this example, 1020/16 goes via the path AVC. So we know as this customer, we go via A, V, reach this final destination autonomous system, and this is where we have this prefix. Okay. And we also know that we try to, well, go take paths that are more specific. So if, for example, we have a second path going this other way here, and then this path may win. We see what this has to do with this topic. The more specific wins, we can have multiple upstreams. So this is also known that yes, we have the path we typically take. We can also have alternative paths, as shown here in this table. So we have path 1 and path 2. And typically we take the first one, but we can also take the other one. So now, what can we do? So more specific wins, shorter paths are typically better. We see here path 1 is the shorter one. This is why we typically take path 1, but if something fails, we can take the other one. So what we could do, for example, here in this autonomous system B, we could do something. We could say, okay, for this, if this is the prefix, then I prepare a special, very short path telling this prefix can go, or you can reach this prefix via me, B, and then you go directly to C. So this is something I could claim. What happens? The customer sees, in this case, oh, I've got two alternative paths. This is one, this is path 2. But in this case, the second one is the shorter one. Oh, that's cool. So let's send all the data for this prefix 1020.00/16 in the direction of provider B. That's okay. Because I don't know that in reality there is still W and X and everything in between. I don't know. It could be the case. How should I know? I mean, that there might be a direct link between B and C, the destination AS. But this is not the case. So yes, B was lying. And why? And what could be a problem? So maybe there's someone sitting there at Y or X or W, and this guy will now see the traffic. Originally, this traffic went through A, V to C, and this bad guy never saw the traffic. But by this announcement from B, we have a shorter path that will lead us the upper way, and now this malicious guy can, for example, read the traffic. This could be a misconfiguration, which happens quite often. Could be malicious. So with or without intent. Does it happen in the real world? Absolutely. So these are just some examples. There are many of them that, for example, Pakistan redirected the worldwide YouTube traffic, or China Telecom, there was a problem, or the corruption of DNS service from Google, and so on. So if you hijack, you remember 8888, so that's a DNS service from Google. And if you then hijack this, and as it says here, so Google DNS, this 8888/32 was hijacked for about 20 minutes, affecting the networks in Brazil and Venezuela. What does it mean? So this affecting, that means that if you ask for a path to this 8888, which is a way to avoid misconfigured DNS or lying DNS, then even this traffic could be redirected. This can be a misconfiguration, so it's not necessarily an evil state or a company or whatever. So what can happen to BGP? So what is the threat model? 3 issues. One is called prefix origin hijacking, one is path manipulation, and one are route leaks. What does it mean? Prefix origin hijacking. The first we'll have a deeper look at. So that means you originate a prefix that you don't own. So you simply claim, oh yeah, sure, I know exactly where this, what was the example, 1020.00. I simply announce this. I say, yeah, I'm responsible for this, so please send me all the traffic. I'm just claiming this. But you're not the owner. What does it mean, owner? As you all know, you have to buy address prefixes, and then you're the owner of the prefix. And we have all these numbering authorities giving you parts of this address space. And now, although I never got this address, I simply claim that I have it. Okay? The second, so that's the first. The second issue is AS path manipulation. That means I change AS paths, as we will see. compared to the original one. That's also something I can do. And then we have a third one, that's a problematic one, because as we will see, we can not easily protect the network from this. It's called route leaks. I will look into this later. So there's a RFC exactly for this, explaining what it means. So basically, if an AS is, I would say, not misconfigured or simply leaking certain routes that do not really follow the official policy. I will come back to this. So so what is the problem? So the original design choice, comparable to DNS, was we have trust between the peers. So where are my peers? So these are my routers. And those routers, they establish our TCP connection and they exchange via BGP routing information. So that was exactly this what I explained, which part of the information you exchange, etc. But this is all based on trust. What does it mean? Any BGP speaker, so someone that announces something, can simply claim to own a prefix. And any of the speakers can modify the path. And the receiver cannot verify the correctness. So if I simply say, this is the path, the receiver has to believe it. If I say, yeah, sure, I'm the owner of this prefix, the receiver has to believe it. So there are some filtering techniques, and so that can be looked up in registry, etc. But this is not really enough today. So this doesn't really help. So how can you protect the path and the origin? So the idea here is we have to secure origin and path, and we have to be able to map prefixes to the to the origin autonomous system. And what we can use is a cryptographic proof. So the real owner should be able to authenticate that really it's me and I'm really the owner of this autonomous system. And the routers then can check if this mapping, if this is correct. We'll see how this works. And we can secure the path information. So we sign the path. So that's for path validation. So no one, also not in between, is able to change the path. Okay, what are the challenges? I mean, we know how to encrypt, we know how to work with certificates, and we've seen this with DNS. But routing, we know that's time critical. DNS, it's a bit more relaxed. Routing, that's critical. So we have certain challenges. So real cryptographic operations, they're quite complex. So in a router, doing all these operations might be a bit complex, but at least it puts some additional load on the routers, but you want to minimize this. Okay, how can this be done? So this is why we now look into this prefix origin validation. So that means we have to validate the origin so that AS cannot simply claim I own this or that prefix. And this is exactly where I come to the RPKI architecture. What does it mean? RPKI, that's the resource public key infrastructure. Here we are again. So again, we are in the context of a public key infrastructure, and that's the basic solution proposed by the IETF. And PKI, okay, you know this. There must be somewhere a root of all of this. IANA. That's why we have the root certificate of all of this. So this RPKI is a system that allows us to verify, to attest the usage of IP addresses and ASNs. This includes, as you can imagine, again, certificates. And all these certificates, like the certificates you have for browsers, for accessing certain web servers, etc., they reflect the hierarchy where this AS is located in the internet. And the idea is, and all these registries they participate, is that you use a certification and then you have your regional registry, and again registration national registries, as we learned when we came to the addresses, where I get my address from, etc. So in addition to giving you the address ranges, you will get a certificate telling you, okay, this is the address, and yes, you're really allowed to use this. So following this hierarchy of distributing the addresses, we have the hierarchy now of the certificates. Everyone participates, and how does this look like? What we here have is the so-called Routing Origination Authorization, ROA. So that means that, okay, this AS, a certain AS, is really allowed to announce, hey, I'm the owner of a certain prefix. So what does this ROA contain? The prefixes and the AS that is allowed to announce the prefixes, and the certificate. And this ROA is then signed with the certificate of the RPKI. So how does it look like? So you have this ROA here, valid for a certain time and for certain prefixes for a specific AS. And this means this AS 123 is allowed to announce certain network ranges, as you see, 1020/16 to 1020/24 and 1890/16 from 1st of October 2012 to 1st of October 2013. So these are the information that basically tells that a certain autonomous system, AS here 123, is allowed to announce certain prefix. This is not the certificate itself. This just shows, okay, I'm allowed to announce this and that. So we also then, this was the ROA here, so that's the proof that I'm allowed to announce it. And then we have the certificates that really prove the ownership of a prefix or an AS number, because we can also cheat with the AS numbers. So we have certificates that really prove I'm the owner of the IP prefix, or I'm really the owner of this AS. The ROAs, they are the proofs that I'm allowed to announce certain prefixes. So this all goes together, and the idea is that all the certificates, including the ROAs, they are published in repositories. All the registries operate a repository. You can also do this on your own. And if you take all the repositories together, you have the overall picture. So how does it work? If we want to check if an AS is allowed to announce a certain prefix, we have to check then the corresponding ROA, and we know, okay, which ROA belongs to certain IP prefix. That's all cryptographically verified. And then the idea here is that if everything is okay, verified, then this is what we call a positive attestation. That means if a ROA exists for a prefix, all announcements of ASs that are not included are considered invalid, because you have a certain AS included, and all the others are automatically invalid, although they might be correct. So it's positive attestation that excludes automatically all the others, and this is one of the problems for some of the providers. So if something is not included, it's automatically considered invalid, might lead to issues. Okay, so that's roughly the principle. And is this used? Yes, continuously growing. This gives examples for IP version 4, the upper graph, and version 6, the lower one. And you see the number of prefixes here shown. It's increasing for the prefixes, but yeah, still far away from covering everything. And also ASs, so AS numbers, you see it's also growing here. It's okay, it's growing, but as always, it's continuously growing, so that's quite nice. So the validation itself using this RPKI consists of 2 steps. That's the validation of the ROAs and the validation of BGP updates. Who gets the BGP updates? That's the router. But the point is, doing the validation of everything, the ROAs on the routers, maybe that's too resource consuming. And this is why typically this is performed at an external cache. And then the OK of the validation is then transferred to the BGP router. So the RPK data has to come to the router, and the router then performs the validation of the updates without any complex additional cryptographic operations. But if you have this 2-layered architecture with one doing this validation, then you have to transfer this result of validation. You have to transfer it to the routers, and there's the question of how. And this is where we have a special protocol. So there's a so-called RPKI RTR protocol, and that manages pushing the valid ROAs from caches to routers. So you don't have to do this on the routers, but basically you push this on the routers, a validation of these ROAs. So you have the repositories where you have them all stored, so from RIPE and from others. So this all together is our global RPKI. You bring this on trusted local caches, and in the end, the results then on the routers. And so what you can store there are then validated prefixes and validated origin ASN. So the routers themselves, they don't have to take care about the validation itself. They simply get the result and see, okay, this is fine, this is validated. So you don't have to do this cryptographic stuff on the router. Okay, and so there are implementations for this of protocols here in C, and they do exactly this, fetching validated prefixes and validated origin ASs from the RPK cache, and sync the validation database, provide interfaces, etc. And this software is open source, and colleagues of mine have done exactly this. Okay, so some minor issues added. Why RPKI is a good idea. We all know that the web is the most dominant application right now on top of the internet. We know that we have TLS to protect the content, yes, but so what happens if we have, for example, forged certificates, or we have problems with certificate authorities? There's a protocol that's called DANE, DNS-based authentication of named entities, and this use certificates for TLS and together in the context with DNSSEC. But rarely deployed, so no Chrome support so far. That has to do something with the type of the encryption, and also no Firefox support. So if something like this is not really used, then we cannot use it. So what else to do? Next slide. Also, the stain is rarely deployed. Validation of forged certificates rarely deployed, and so this can be used also if you do prefix hijacking to, in the end, compromise web services. So TLS only protects, yes, end-to-end, but that's not enough. So you can basically kill a web service. You can redirect the traffic, so you cannot use it if the attacker is able to manipulate the routing. So that's the problem, that attackers can redirect the traffic to a web server, and then the web server is not accessible anymore. So in the end, if an attacker knows, and this is typically the case, that the pages themselves, they are protected by TLS, then you can try attacking the path, the way of the data towards the server. So you can perform denial of service attacks. You can even perform attacks that do not affect all the clients. So you can just manipulate some of the paths, and the servers, the web servers, don't notice anything. It's just no data reaching the servers because someone did something to the path. And this is one of the reasons why you really have to protect the paths. And the end-to-end encryption will not help here, will not help for playing with the paths. We had a third issue with this, with the threat model, and that was route leaks. So basically, this can be said, it's announcing prefixes conflicting with what you expect from an autonomous system. So this route leak, that's propagation, as the IETF says, propagation of routing announcements beyond their intended scope. So basically a violation of the intended policies of the receiver, the sender, of any the other ASs. And the result could be then a redirection again of traffic through a path you have not really intended. And this helps, again, eavesdropping, and you can create overload or a black hole, so in the end. So routing leaks could be accidental, malicious, but most of them typically misconfigurations. So how can this be done? So you as a provider B, you could announce certain paths telling that, okay, telling two different paths where maybe one of the paths doesn't make sense from a policy point of view. So that a provider, for example, announces a path like this one, that's a shorter one. So this would be taken, but announcing a path across a customer. So if a customer has the two providers, usually the policies never ever, and this is what we learned, never ever route the traffic across a customer's network. So you'd always take the other path. But a provider could do this, and that's a routing leak. But the problem is, what can we do? Nothing. So this prefix origin validation or AS path validation doesn't help, because B, is allowed to, announce this path. Everything is fine. The origin, everything is fine. So these route leaks, they undermine the policy assumptions. So typically you do not route across a customer. But RPKI can do nothing against this. Why don't we have RPKI everywhere? Well, there are some reasons, some political reasons. Who do we trust? We saw in our hierarchy that we have the trust, we have the root certificate, and then we have different registries, the regional internet registries, and these are our trust anchors. And so do we trust them? Maybe more than some of the countries, so some governments. But sometimes governments don't like this, and also some local law may interfere with this. And so there are some political reasons. Also, this is all out of the control of operators, autonomous systems. So this is all basically controlled then by the registries. And there are also business reasons. As I said, it's a positive attestation model. So if someone says yes and can prove this, I'm the one who can really announce this prefix, this excludes automatically all the others. And this might be a problem. So you have to know basically in advance. So prefix and aliases, and then this is also all cryptographically protected. And if you change something, it doesn't fit anymore, which is then reflected in it doesn't work anymore. And so this might be a problem. Then always cost and complexity and yet another protocol and yet another infrastructure. And if there's some misconfiguration, again, this causes additional problems. And this all slows down the deployment. You saw increasing, yes, but far from being fully deployed everywhere. So go back to BGP, and then you will understand why it's that easy to announce false paths. Why is it so easy to lie? We saw RPKI, or this was a very short first brief introduction, but we saw that we can solve some of the issues, but we cannot solve all the problems in this context with BGP. So which problem we cannot solve here? What is the idea of this ROA? What can be done there? And why can RPKI also help in the web ecosystem? Yes, we have TLS, but TLS only does some part. An attacker could do a bit more where TLS is of no help. And then finally, why don't we have RPKI everywhere? What could be reasons for not using besides politics and business? Politics and business is always a reason, but maybe there are some more reasons.